Yeah, they type 6.6. So they went to the type 3.3 and then they went to just one.
Okay, we got a couple minutes, but we're going to start because I've got to take off a few minutes early. So, last time I hope that the corrosion guy, Randy, was worth listening to. He's one of my favorite. I don't do guest lectures almost, in this class not at all, except for Randy, because he's just seen it all. I hope he didn't say anything terribly inappropriate. I'm always like, I'm sitting on pins and needles a little bit when he comes and talks. Hope it was great. He's like, corrosion is a big deal, and like the way that he talks about it, I think is accessible to all people. And I'm glad that this year we actually had it after we learned about electrochemistry, because you already know about why there has to be salt there, why you have to have the anode and the cathode and all that jazz. Okay, so today we'll pick up where I left off like a while ago, which was we just got to this concept of engineering stress and engineering strain versus true stress and true strain. And the big difference, if you remember, is that engineering stress is if you're pulling on something, you know what its original cross-sectional area was, but we don't know what the instantaneous cross-sectional area is. If you do know that, then you could calculate the true stress, which is why when something starts to neck down, instead of it actually getting weaker, it's actually getting stronger. The more you pull on something, the more you plastically deform it. Almost all materials get stronger due to something called cold working, which we'll get to later. But you only see that if you take into account the cross-sectional area and how stress is actually rising. So this time we're gonna talk about one last thing on these stress versus strain curves, which is resilience and toughness. And then we'll talk about bending, and that's how they test most ceramics actually, is they bend them. We'll talk about what happens if you have porosity or you change temperature, you do the strain rate, how does that change some of these things we've already discussed. And then we'll get into non-Newtonian viscoelastic response, things like rubber or like silly putty, right? Why do they behave the way they do? How do we model it? How do we account for it as engineers? And then, you know, if we have time, we'll talk about hardness. And if we're really early on time, we'll get to variability, but I'll bet that'll be next time. Okay, so last thing we could do, or last thing from last time was ductility. And I think we mentioned this, that ductility, it's hard for us to say ductility, be quantitative about it, because we just know that something's easy to bend or it isn't, or it can bend a lot or it can't. So we need a way to describe ductility in a quantitative way. And the way we do it is we say either percent elongation, right? So you take L final minus L initial divided by the L initial. Whatever that is at fracture, that's your ductility, right? So it's a strain, but it's a strain at a certain condition, right? You can do the same thing with reduction in area. That's another measure of ductility, right? So now if you've got a material, two different materials, say a brittle one and a ductile one, their curves might look something like this, where you plotted stress against strain, and you see that one of them has basically no plastic response. It's elastic and then a tiny bit of plastic before it breaks. So the question is, what's the area under the curve, right? If you think back to calculus, when they said, you know, distance versus time, what was the area under the curve? Right? You multiply the units of the two axes, right? This should ring a bell, right? So in this case, I'm here to tell you that the area under the curve is the absorbed energy, and yet you've got stress multiplied by something with no units. So how's that all right, right? So the only way that that works is if we recognize that stress, right, that's Newton per meter squared, right? That's a Pascal, right? So that's stress. So, but Newton itself equals a joule per meter. So overall, we end up with joules per meter cubed, right? So it actually is an energy per some volume, right? Whatever you're testing has some volume. This is saying how much energy gets stored in that component as you deform it, right? Either you deform it elastically, and we call that this red area, we call that resilience, or you call it the total area under even the plastic section, which would be the toughness, right? So resilience, I think the way to remember this, somebody that's resilient, like somebody who survives cancer, beats it, and they're right back, right? They're resilient. It goes back to how it was before, right? That's a resilient person. Same thing with polymers or ceramics or metals, right? If it's resilient, there's no permanent damage, right? It bounces back, right? So that's the resilience, is the area under the curve for the elastic region. Whereas toughness, it gets beat up and it just keeps going anyways, right? That's accounting for plastic deformation. So materials that either have a high or a low resilience or toughness are useful for lots and lots of applications, right? Somebody help me think of an application for, or maybe turn to a neighbor and take a guess, why would you want a material with a high resilience? Can you think of an application for high resilience? Okay, who thinks they've got a good one? I heard bungee jump over here. So that's actually a really good one. A bungee jumping cable, if you jump off of that, you want it to stretch, like you want deformation, but so you want to be able to store lots of energy, meaning that you're going to convert lots of your kinetic energy into potential energy. It stretches this thing basically, right? But you definitely want it to go back where it started with. Actually a little bit less. You don't want it to go back perfectly, which nothing will, right? You don't want to hit the platform. But yeah, that's an example. Anything else? What else comes to mind? High resilience. Matt? Shocks are a great one, right? So springs, that's a classic example. In your physics class, once upon a time, they probably showed you this demo. And the spring constant, basically how much energy it could store, that's just measuring the resilience of the spring. But yeah, it's another great one. Now how about toughness? Where do we care about toughness? Any thoughts? Toughness, remember, that's where we're saying we're okay with plastic deformation. Is it Steve?
Yeah. We got a phone screen.
Yeah, exactly, right? It'd be better if it didn't break at all, but if it's going to have to bend, you'd rather it not totally shatter and break, right? You're trying to avoid fracture. If it's still bent afterwards, phone screens, that's a tough one. But there's certainly a lot of things. Got another one, Shannon?
Your car in an accident?
Exactly, right? If it's deformed, maybe that's okay, right? You're gonna have to get it replaced. What you don't want is it to fracture entirely, right? That could be very bad, right? So that's area under the curve. You can literally quantify how much energy got absorbed in that deformation, whether it's a collision that caused deformation or whether it's a controlled experiment where you're stretching it. We can quantify how much energy goes into it from this curve. And I think we'll see this on the next homework I assign. I'll actually give you a curve, and I'm gonna have you, in a as sophisticated way as possible, take the area under the curve, which means integral. And when you think integral, that means you're going to have to find an expression for one of these things. So you're going to have to do some point fitting in Excel or whatever. Still not fixed, surprisingly. Okay, I will speak up. Yeah, Danny?
So on this graph, did you say the resilience is up until it starts bending like this? Like the red point?
Anything non-permanent, we'd call, that's the area under the curve, that's the resilience.
Okay.
Now technically this, you know, I guess that's below the 0.2%, I guess. So they'd still call that resilience. Okay. Okay, again, it would just be the area under the curve. Just mentioned that. Toughness, lots and lots of applications for toughness. I went to grad school at UCSB, and they work a lot on armor there. So armor for ships, armor for vehicles, right? In that case, you've got a blast, right? So you've got a lot of energy coming at the vehicle or the soldier or whatever it is, and you want to dissipate that energy rather than fracture, right? So they have all sorts of layered materials. They actually took a page out of mollusks and like clams and stuff, because birds do this. Like birds grab the clam, they fly in the air, and they drop it on rocks to get the sweet, sweet, oozy goodness out of it, right? So they took the same page out of it. They said, all right, what if we did the same thing as clams? And you take a hard layer, like a ceramic, and then you put a polymer layer, something compliant in between, and you do a lot of layers like that. And that very simple layering is actually a great way to introduce toughness into materials, right? It gives you much more plastic deformation before the thing breaks. Because individual sheets of hard things can break without the entire thing breaking, right? So a lot of these things will be calcium carbonate, it's a ceramic, followed by some biopolymer between them. And material science has taken a big page from that. They've invented a lot of things mirrored off of that. Okay, somebody last time said, what if you load something and you load it into the plastic regime, but then you let it go? Does it have any of its elastic character left? It does, right? So let's say you loaded it out to that point. When you let go, it will still go back some amount, which is whatever your original modulus gave you, right? So it'll be unloaded. And then when you start it up again, it'll pick up where it left off. It'll start from right here, and it'll go right into the plastic regime after it overcomes a very small elastic regime, okay? Okay, let's talk about ceramics. I think we mentioned last time that they're hard to test. It doesn't make sense to take your vice grips and clamp onto your dinner plate because it would just break right where you grabbed on. So how do they test these things? The best thing that they do is bend testing. That's sort of a good way to get around it, because if you bend something, if this is a piece of ceramic I want to test, I can take it and I put maybe 2 supports below that are closer together and 2 supports above, like so. And if I apply a force on these 4 points, I can produce bending, which, think about what it's doing. It's actually placing this bottom side under compression, but the top side's under tension. So it still gives you a strength of tension, but it does so without having to clamp onto it anywhere, right? You just load it. You have to make sure it's like evenly on there and all that, right? But bend tests are by far the way more common way to test strength in ceramics. It is not the same as a tensile stress. It is now what's called the modulus of rupture, right? So the modulus rupture, here's the formula for it, right? If you have a 3-bend configuration, you need to know how far apart these are, what your force is on there. You have to know the thickness and the height of your sample, and you calculate this MOR, modulus of rupture. Not the same thing as tensile strength, but it's a pretty great thing to know because it's a decent stand-in, right? So the question is, if you have 2 scenarios, right? Let's say you've got these 2 scenarios right here. 3-point bend, which would be like 2 below and 1 above, right? So I don't know how to do this with hands, right? It'd be like that, where I'm bending it like that. Or 4-point, which I just showed you. Will you get the same value, right? So this will be our clicker question for the day. Pause that. Everyone get a chance to log in real quick. The question is, will the bend strength be lower for 3-point bend or for 4-point bend? And you don't need to know any formulas for this.
Bend strength is like how much?
Yeah. Okay, get your answers in. 30 seconds. Okay. Okay. The majority thinks that 3-point bending will have a lower strength. And that's actually wrong. It's actually 4-point, right? After class, I'll make this one go either way. I'm not trying to trick people out of losing points, right? So help me understand, why on earth would 4-point, somebody who voted for 4, who thinks they might have an understanding, why could that give you a lower strength? And what's your rationale? Anybody have a guess? Kylie.
I did a lot of playing with my pencil.
Okay.
I realized that, like, if you have a 4-point, the point is going to break in the middle, right? And so it seems like where you're applying the force, it just has a bigger lever to that point than if you have the pivot right in the center. Really great way to think about it. And one thing you said where it's going to break in the middle is sort of the key feature there. You said it's going to break in the middle. Why does it commonly, but not always, break in the middle? That's really getting to the heart of this question. Why does it commonly, but not always, break in the middle? If you take a pencil, you start bending it, it could break, anywhere, but it'll most likely break in the middle. How come? In the back.
It stays straight nearest the supports, right? So like as that beam bends, you can say like there's a tangent to the bend at those points. So like if you only had 2 points, it would break in the middle, because that's where you're going to have the most deflection.
Okay, that's a good guess. That's a good guess. Any other questions? Let's do Eric and then maybe one more thing.
So I'm thinking it just has something to do with leverage, because you have a longer lever arm for the
yeah.
potential.
You've taken statics by now, mechanical engineers. So tell me, what is the moment of inertia? And then tell me what torque is, right? Torque is, you've got a point of rotation, right? In this case, we're not actually rotating this thing, but we're causing part of it to rotate, right? Because part of it's starting to bend, right? So if you want more torque, what do if you have the same force? You'd move it further away. So actually, it produces what's called a bending moment, which you would have seen in statics, right? So the force might look something like this, right? So here's the force diagram. You're applying forces up on these points, down on there, right? So you've got your force diagram, right? In this case, you've got no force in the middle, right? It's canceled out. And then if you look at the bending moment diagram, in a 3-point, the bending moment actually increases until you get to the middle, and then it decreases for the 3-point bend. But for 4-point bend, it increases here, and if you actually do the calculation of 4-point bending, this is all at a maximum, right? So think what I just said, like in the 3-point bending case, you've got one point, one line, I guess it's a plane running through your sample, and on that plane you have maximum bending moment. But in 4-point bending, you now have a 3-dimensional area, much larger than a plane, right? You have a volume which is experiencing maximum bending moment. Now, the way to understand which one produces lower or higher strength is to remember that ceramics break due to their largest, most what we call critical flaw, right? And when you make these things, that critical flaw could be anywhere, right? This critical flaw could be right here, right? In the case of 4-point bending, that critical flaw is within the region of highest bending moment, right? In this case, it's lower, so that critical flaw may not break because the bending moment is so small, right? So it all comes down to what volume of your sample is experiencing the most extreme conditions. And in 4-point bending, you expose a larger segment of your sample to that. So which one's better or worse? It just depends, right? If you want to know, like, basically, we'll have to come back to this, I think, next time before we can answer that question, which one's better, because neither of these are very good. They're both numbers, right? 3-point bending, 4-point bending, they're going to report, okay, 3-point bending had 500 megapascal bending modulus, right? And then when they did it in 4-point, it was maybe 400. So you would say, so what? What I'm building is neither in a 3-point or a 4-point configuration. It's something very different. It's maybe like a shock or a spring or a ball bearing or something. How do I translate these simple lab tests, which are easy to do on little bars, into something meaningful, like an object that has a weird shape? and we'll get to that next time. Okay? But again, this comes back to the fact that flaws could be anywhere, and it's all about the largest flaw. Statistics says there's some largest flaw in there that will cause this to break, and if that's at the region of your highest bending moment, it'll break sooner. So you have a lower strength, right? So ceramics are oftentimes not fully dense. I think we mentioned this last time, but they are made up of, when you first make ceramics, you can learn all about it in my class next semester if you want, but you start with little tiny particles, then you put them together, right? We press them in like just a regular garage, sort of uniaxial press, and that's not very well bonded. That's just sort of clumped together like my 5-year-old making a sand castle. If you want to then bond that, you have to put that in the furnace and cause those particles to grow into one another. And again, we mentioned that back in the 50s, bubble rafts were all the rave. It was no different with sintering. They could actually simulate sintering with these bubble rafts, if it ever pulls up. Maybe. The internet. So they would take these things, they'd make a bunch of little bubble rafts, and then they'd remove the cup from underneath the surface of water, and over time these things would slowly come together, right? So they're not being pushed together by like an outside force. That's literally what? That's minimization of surface energy, right? It says we'd rather have fewer surfaces. And so these things, given time and energy, they will come together. And so they do this with a whole bunch of different things, right? And you can see that they're not even quite lined up, right? They have different orientations ever so slightly. So there are grain boundaries between them. And yet these regions that don't quite go away, that's pores. When you work with ceramics, getting rid of those pores is the biggest challenge. Getting rid of those pores is really hard to do. So, if you don't get rid of them all, and you normally don't, it's very, very hard to get 100% dense ceramics. What do? They're going to degrade your mechanical properties, right? So there's a number of different expressions out there. One of them is right here, the elastic modulus and the flexural strength. This shows what happens to them if you have residual porosity. So P is going to be your porosity. That's going to be your fraction of porosity, a number between 0 and 1, right? So it'll take whatever your original modulus was for a fully dense material, and then this is obviously just an analytical expression that fits data. This is not like from first principles explaining what's going on. This is just a pretty good fit to data for most ceramic materials. Same thing with your flexural strength. That's the same thing as your modulus of rupture. You'd have your completely dense value, and then you're going to have to modify it by this exponential of negative NP, where N is going to be a constant you have to know for your system, and P will be your porosity, right? So modulus does something like this. More and more porosity, you start losing modulus. Same thing with strength. And I think the right way to think of it is that if you have porosity, you're really just effectively decreasing your cross-sectional area because you've got some of your area that's not bearing any load. Therefore, the area that's left over is now a reduced cross-sectional area. Therefore, it's experiencing a higher stress. Therefore, it breaks at a lower apparent stress. Right? All right, polymers. Polymers, when we started a couple chapters ago with the banana demo, we talked about how both temperature and strain rate can produce huge differences, particularly in polymers. You can make a polymer which is normally, you think of it as very ductile, extremely brittle if you pull on it very quickly, right? So the students in my MSE 2010 class for the last week for their lab, they took polymer dog bones, they put it in liquid nitrogen, it breaks obviously very brittly, but also if you take that thing and just pull on it really quickly, it'll break nice and cleanly, whereas you pull it slowly, it might stretch all the way to the limits of the Instron test frame. It'll go all the way as far as it can go, right? So temperature and strain rate are two very important variables, but there's another one, there's also environment, right? You could have something that's corroding it or oxidizing it or something, but all these things will influence your mechanical properties, right? And you could go from a material that you expect to be ductile, and all of a sudden it behaves in a brittle way, or vice versa. And it's pretty dramatic, right? This is for PMMA. That's it's commonly used in dental ceramics. It's like a bonding adhesive. So PMMA is a type of polymer. If you test it at 40 degrees Fahrenheit right here, it is very brittle, right? That's very cold. This thing looks like a ceramic, right? Same thing now at 68, 86, 104, 122, 140. Completely goes from ceramic to what looks like a rubber down here, right? It's actually probably flowing at that point. It's almost melting. Yeah, it extends all the way to 1.3, so over 100% elongation. So massively extends just based on the temperature, right? Some things to have in mind numbers-wise is that for polymers, modulus of elasticity, it's generally less than 4 gigapascals. Whereas metals are, several orders of magnitude larger, 100, 400 or so. Polymers have tensile strengths, which are way lower than other ones, right? 100 megapascals, they're not very strong. We work with these things, we know that that's the case. Metals can be, again, several orders of magnitude larger. But percent elongation can be as high as 1,000% in polymers, whereas metals, it's tough to get it over 100% elongation. You have to have a very ductile metal to get over 100%. So why can they deform so much? Well, it's useful to think of it in terms of the spaghetti strands that form polymer molecules, right? So here's our molecule. If you're, this is our polymer, I guess, material. As you're pulling on it in a vertical direction, initially from the molten state, as they sometimes call it, if you like injection mold this thing, the strands are going to be every which way. They're going to be randomly oriented. But as you start to pull on it, the way that it's able to deform is literally by these chains starting to orient, and then it's going to thin down and get, necking going on. And then it'll actually, this is actually called drawing. And drawing is when your polymer chains now start really lining up one against another. And because they can do that, you can get really high amounts of deformation. The reason why it doesn't break is because these are weak bonds. They're just van der Waals bonds. In a ceramic or a metal, breaking bonds releases a lot of energy, and it's often so much so that it's catastrophic. It keeps on breaking more and more bonds. These things are low energy bonds, so breaking them is not as hard, right? Now, if you do this, imagine what would happen. As you pull this thing, these fibers are orienting themselves. What do you think is happening to the strength? Any thoughts? Turn to your neighbor. What should be happening to the strength as you orient this thing, pulling on it more and more and more? Okay, I'm hearing stronger, which it is. It's getting stronger. Anybody have a guess why? Why is this thing strengthening? There's sort of two reasons I can think of. Simone? You're ordering it. Why would that lead to higher strength? That's right. Yeah, if you line these things up more, now you've got more region whereby they can lie next to each other, right? You went from this random spaghetti to now lining up. Now these things can experience a van der Waals bond over a longer length of the chain, right? So it's gotten stronger. And you're also starting to pull a little bit more on the actual backbone, right? So crystallinity goes up, van der Waals forces go up, you're strengthening these things. So as you pull on taffy, even though the cross-sectional area is reducing, which makes it feel like it's getting easier to pull apart, technically, if you were to normalize for cross-sectional area, it's getting quite a bit stronger because the bonding is increasing as you do this, right? So this happens all the time with polymers. Whenever you load them, they, at some time and time scale, these polymer chains will start to relax. They're not actually relaxing, they're changing their direction. We call it stress relaxation though, because the polymer chains are changing their orientation to accommodate for the stress that they're experiencing. Do you have a comment, Matt?
Yeah, would that explain why with like for a rubber band, for example, it's really easy to pull, but at a point it gets a lot harder to
That's exactly it. Because the cross-sectional area doesn't change super dramatically. It just gets a lot harder because sooner or later, in a rubber band, the polymer chains aren't totally free to slide past each other. They're cross-linked, remember? And when it gets really hard to pull, you're pulling on breaking things that are cross-linked, and those are covalent bonds. Those aren't weak van der Waals bonds. Those are covalent bonds. Kylie?
So it breaks van der Waals bonds through your end, and then it reforms that one through your
Exactly.
end, right?
And it forms them better because now the chains are nice and lined up.
So then why, when you let go of it, if it's pretty happy where it is and very well bonded, why does it relax?
It won't always. Oftentimes polymers, if you stretch them, it's permanently deformed because the polymers don't want to go back at that point. I mean, there's an entropic component that says go back, and that's why rubber bands go back. But yeah, you've increased bonding. So it's going to be a balance between enthalpy, which has to do with the bonds, and entropy, which has to do with disorder. And it strikes a balance. Did I see another hand somewhere? Yeah,
I
Eric?
was wondering, with the chain length, does a rubber that has longer chains, is that typically more stretchy? Because it's allowed to move more before it starts?
I'll say I won't know for sure, but my hunch is that it's not normally a function of molecular weight. It's a degree of cross-linking. Because cross-linking sort of nullifies chain length. Because instead of having something that's super, super long, it's how often is this thing tied together to another one. Yeah. So degree of cross-linking, I think, is a much more prevalent one, but I could be wrong on that. That's a guess on my part. Okay, so with polymers, because these things can respond, and it might happen quickly or it might happen slowly, depending on how easily these polymers can move around each other, and it'll depending on the system, you get what's called viscoelastic behavior. Viscoelastic means that normally, you apply a stress, right? Stress versus time. Maybe this is the stress you applied. You pulled on something, then you let go, right? And it's all like instantaneous, right? Instantaneous load applied, instantaneous load dropped, right? But you don't see an instantaneous or an elastic response, meaning an instantaneous elastic and then instantaneous recovery, right? Instead, you see this, there's some component that's elastic, but then it just sort of like goes up and sort of asymptotes after some period of time, right? So there's gonna be some time associated with this viscoelastic response. And then when you let it go, you'll get rid of your elastic component, but then it's gonna slowly maybe bleed off, right? So that is viscoelastic response, okay? Let's talk more about that in just a second. But first off, all right, we said that temperature and strain rate can both influence this, right? Mechanical properties. So how do you account for both of them? You've got to fix one while you test the other, right? So for example, you would pick a single temperature and then you test a whole bunch of strain rates. Or you pick one strain rate and then you take a whole bunch of different temperatures, right? You have to fix one and vary the other since both of these things are coupled. And this is ignoring other effects like corrosive atmospheres or anything else like that. We're just talking about strain rate and temperature, right? And so when you do that, that's when you get plots for what are called these stress relaxation equations. So let's say you took a polymer, I took this plastic bag and I pull on it, right? And right now it's maybe supporting one, whatever this force is I'm applying to it. Call it like a Pascal, I don't know what I'm doing, right? It's got some force. But if I leave this long enough, it gets easier and easier for me to hold this an equal distance apart because the polymer chains are like stretching out and lining up and it's just deforming, right? And then the stress that I'm having to apply to it to maintain some deformation, it's going down. So that's why they call it stress relaxation. The stress that you put something under is going down and down and down, right? So if you have a gasket, a polymer gasket on an engine, and you need it to be torqued to a certain, torque, right? That means it's experiencing a certain stress, but if that polymer can slowly flatten out and squish over time, it's not going to maintain the same stress that you torqued it to, right? So gaskets, polymers aren't great gaskets for that reason. Some of them are okay, but they actually use micas and they use some other things for gaskets because they don't experience stress relaxation, right? To have the full expression for stress relaxation, so this would be stress, this would be as a function of time and temperature technically. You're going to take your stress under the initial condition, which is at the glassy transition temperature. Or no, this is your initial stress, excuse me. So at time t equals 0 seconds in, there's some stress that the polymer is supporting. It's going to be reduced by whatever the modulus of your polymer is, however long it's going, t, divided by eta, and eta will be your viscosity. We're going to talk about that next chapter, so let's come back to this equation next chapter. So at any given time, as a function of time, you have to calculate your modulus, and it's changing, right? The modulus is changing. So they would do an experiment like this. They would maybe vary different temperatures, and they would capture stress relaxation modulus by basically measuring the stress as a function of time in a sample by when you hold some static load, some static displacement, right? And then they take all these different temperatures and they piece them together to make a plot like this. This is known as a glassy transition curve, right? What it's showing you is it's showing you what the modulus is, right? Resistance to deformation, that's the elastic modulus, as a function of time held, right? You could do the same thing with temperature, right? This is both either for time or for temperature, right? So this is your master curve. So basically it says if you go to negative 80, you've got a really high modulus. It's behaving like a ceramic, right? It's brittle. It takes a lot of load. It doesn't deform very much. But by the time you're up to positive 80 degrees, that modulus is super, super low, right? And most polymers, not all, but most will experience this trend where they go down, they plateau, and they go down. So that is the glassy transition. That's a hallmark of a glassy polymer, something that goes through that glassy transition where it goes from a ceramic to sort of a rubbery plateau to now something that's almost even flowing. It might be flowing actually, right? So again, glassy state, glassy transition is going to be somewhere around here where it leaves the glassy state into the leathery, rubbery flow, finally liquid region, right? So these are very handy plots. These obviously depend on a specific strain rate, right? Because we said strain rate and temperature can give you the same thing. So this would need to be reported at a certain strain rate, but these are typically reported for materials. For polyethylene, polypropylene, you can look these up and you'll know, hey, this polymer, even though in our daily life it seems really rubbery and plastic, turns out under these conditions it's going to be very brittle maybe, okay? And this should make sense because at lower temperatures, the chains get sort of frozen in position. The chains aren't free to sort of slide past one another and elongate. And so therefore, if they can't do that, it's no longer flowing, it's gotten brittle, right? So if we consider 4 different types of polymers, let's say crystalline, cross-linked, low and high molecular weight, atactic polymers, right? We could even try and estimate what these curves might look like, right? So this is, again, this is modulus, and it's as a function of, you know, time and temperature and all that. And then here's temperature. If you take a low molecular weight polymer, let's say this one's red, it might look something like this, right? Now, if you went to a high molecular weight, how might this drawing look a little bit different? What would high molecular weight do to this sort of paradigm? Matt? What's the rationale? I think you're right. Why would it, though?
Because it would take a higher temperature to have it reach the plateau, so it would take a higher temperature to have the same effect on the...
Yeah, I think what's happening here is you're going from leathery, so it's still bonded together towards here where it's flowing past one another. So to go from that, basically this has to do with the van der Waals forces, right? So if you go to higher molecular weight, that's longer chains. That means higher, generally speaking, it's higher bonding, right? So yeah, it would look very, very similar, maybe, but it would go out a little further, maybe something like that, right? That maybe would be high molecular weight. How might crystalline look, a crystalline polymer? I'll have to double check. I didn't bring my notes, actually. I'll bring this next time. I think I know what to do. I don't want to draw it incorrectly, though. And then cross-linked. How would cross-linked look different as well, right? So ask yourself this. Will a cross-linked polymer ever flow? No. You heat up a piece of rubber, it doesn't melt, it burns, right? So it's never going to flow. So it's going to just keep on going, right? And I believe a crystalline is just going to do something like that, but I will come back with that and double check it next time. Okay? So I'll come back to that. That's the glassy transition curve. It's very useful. This is something, again, that's commonly reported, especially if you have a polymer. You'll see a spec sheet that basically tells you how's this polymer going to behave. Yeah?
By glassy state with polymers, are we just talking about like the disordered arrangement of polymer chains?
Yeah, think of glassy as frozen in place is maybe another way to think of it. Right?
Just non-crystalline? I don't understand how it can be something crystalline and glassy.
How something can be crystalline and glassy? So it's glass, like a glass is a you could say ceramics, right? Ceramics are no plastic deformation, right? High modulus. That's what they mean by glass. Glass is a ceramic, so it's behaving like a glass. That's all. Now, thing to note here, this is against temperature. You could produce this exact same thing against strain rate, right? Because we know that both strain rate and temperature can give us the same behavior in polymers. How is strain rate coming in? Well, think, if you apply a load very, very quickly, are you giving the polymers time to arrange themselves? No, right? So the same thing. There's some critical strain rate where it just behaves like a glass, right? And there's some strain rate, if you do it slow enough, it'll actually flow, right? If you're pulling something really slow, it'll just keep on stretching all day long for many materials, right? So it's not just temperature here. You could just as easily replace this by strain rate, right? And produce a similar curve. Yeah, Matt?
So with the, going back to the graph, so for the low molecular and the high molecular, why is it that on the upper part for the plateau that it's the same? Wouldn't I think that the high molecular would have a little bit further out?
It might also. I'll double check the drawing. We'll come back next time and talk about it.
Just a little bit stretched out.
I think this really has to do with polymer. So this is rubber. So this is deformation really setting in. So I would guess it's more manifest here, but I'll double check that next class. Any questions about this? We've got just a few minutes left before I've got to take off. I've got to go give a talk. So viscoelastic creep. Polymers, we talked about creep before. That's plastic deformation that occurs over time, right? So you're not changing the load, right? The load stays the same, but deformation slowly occurs. Polymers are particularly susceptible to this because they're so weakly bound together. All it takes is chains to slide past each other. So if you're going to leave something sitting for a long time, say like a car tire that's not heavily cross-linked, you might want to put one of these flat stoppers on it that prevents the formation of flat spots, which is just creep. That's creep in the tire, right? Now, cross-linking should prevent that to some degree, but clearly not enough that there's a market for these things, right? Did people buy these things?
Oh yeah,
they probably exist. Yeah, classic cars or something. Okay, the last thing I'm going to get to today will be hardness. One other way to measure a material's mechanical response, and there's loads and loads of ways. We're not covering all of them. One last way we're going to talk about today is hardness. Hardness is, by definition, sort of a material's resistance to localized plastic deformation. In other words, scratches and dents, right? So if you have a piece of steel versus copper or gold, right? People know that, like, they check if something gold, they bite it, right? And if they can indent it, they say, aha, it's gold. It's not something else, right? So that's just them doing a very, very kludgy hardness test, right? Nowadays, we've got much better ways to do hardness tests, but the principle is pretty much the same. You take an indenter, instead of your tooth, you use something that has some pre-described shape. Oftentimes it's a diamond, or if it's Brunel, then it's a sphere. If it's Vickers, then it's a diamond, right? You take that, and under a very specific load, you let it press into the sample under some load. You then remove it, and you either observe how deep it went in, or sometimes they'll actually take a microscope lens and swap it around and look at it, and they'll take a look at how big of the indent it is in terms of area. Either of those then can be correlated to a hardness value, and basically the higher the hardness, the more resistant it is to resisting deformation on a small scale. To do this right, there's lots of things that needs to be a flat surface, obviously. You want to get rid of any surface oxide layer. Otherwise, you're testing now the oxide layer plus the metal underneath it. Now it's going to behave differently than just the metal. So there's a lot more to that. And that is all we'll do today. But next time, we'll pick up with how do we deal with variability in data. So you test one sample, and it doesn't change very much, but you test 20, and you've got a pretty big range. How do we deal with that as engineers? Is what we'll pick up next time. You don't.